good. Let's get started. Welcome, everyone. So I'm going to talk a little bit about research that I've been doing actually for the better part of 10, 15 years. I know it sounds a bit pathetic. I started out with working on carbon capture and storage, carbon storage. So that's the first part of my talk. And if there's still time, I'll move over and talk a little bit about hydrogen storage and why I switched kind of camps. Okay. So first, right, carbon storage. What is that about? Perhaps some of you have already seen this slide before. In a nutshell, yeah, awesome, it works. In a nutshell, you need a point source, right, like a coal-fired power plant, okay, that provides you the CO2 carbon. You capture that, and then inject, let's say, you dump it down in the underground. Okay, and there are different ways or different reservoirs where you can actually do that, and the one I'd like to focus, because there's a little bit, or there's most fun in geochemical and chemical terms, is number 6, here, over there. Right, is basalts, okay? So I've been working actually in the broad field of carbon storage in the solids. Okay, however, before I actually start talking about it, I'd like to point something out. Whatever you do, however you want to store the CO2, other than basalts, you run into some hitch. And the hitch is rather the fact that we're talking about a gas after all, carbon dioxide, right? And at a certain volume. And so when you start injecting it, at depth, kilometers of depth, okay? The good news is you're going to increase its density. So you'll see how the density evolves as a function of the depth at which you inject, okay? And so, so it increases depth, it reaches, a threshold where it changes its phase from gaseous into supercritical, and then you can increase still, so it becomes basically a quasi-liquid, and you increase still its density, and you end up here around 700 kilograms per cubic meters, which is 0.7 kilograms per liters. So it's less dense than water. And that's very important, because what it means is wherever you inject it, okay, it has a buoyant effect. It's going to move upwards, migrate upwards. And this is why you always need sort of really a tight cap rock, a tight seal, as we call it, okay? Not, however, when it comes to the salt. And now we're going into the nitty-gritty chemistry a little bit, bear with me. And that is, we're taking our gas here. What we do, though, is we carbonate it. We solve it in water. We're creating carbonic acid. That's a very straightforward process. That's a very weak acid. Part of that weak acid will dissociate and create bicarbonate and ions, right, solutes and protons, okay? So basically what we came up with is that we dissolved CO2 in groundwater, and it is the dissolved, the carbonated groundwater that we injected at depth into a basaltic terrain. We're creating, as you know, and we've seen now, we're creating a low pH, and with low pH I mean roughly 3.5 to 4, so it's not super acidic after all. Anyway, we inject it, and it will react with a reservoir rock, with the basalt, okay? The basalt is rich in divalent cations, and the reaction will increase the pH, and we will end up with carbonates. Okay, so here it is. That's your bicarbonate that you created to the dissociation of carbonic acid. Here's your calcium that is provided by the rock, and you end up with forming calcium carbonate, as Franka pointed out. Okay, so we're doing similar things, but we couldn't care less actually about the way we're creating, or whether this is vaterite, aragonite, or calcite as isomorph. Okay, as long as we're able, and that's the key point, we're starting out with gas and we're ending up with a solid. That's a massive difference to carbon storage in saline aquifers or abandoned gas and oil reservoirs where the supercritical, where the CO2 is supercritical and has always to drive upwards. Okay, so in a more flippant way, we're creating our Perrier water, right? We know that, like Coke, and then we let it react with our basalt, and we're creating, a solid. Good, lovely. To test that hypothesis, while it was in 2006, 50 years ago, roughly, a CarbFix was created. So that's an international consortium, and looked at all these different aspects of this sequestration, as we like to call it, okay? And I'm going to focus on the field injection study. That's most fun. But I want you to understand there was a lot of chemistry and geochemistry and lab work involved, also looking at hydrology, the modeling, and so on and so forth, and tracer tests. Okay, good. So it's not really when we went to CarbFix
project played out in Iceland. Okay, so that's a satellite photo of Iceland. That's where the capital is, Reykjavik, and the injection site was half an hour drive away. Okay, that's bird's eye view of the injection site. Why? Because over here there is a geothermal power plant, and that geothermal power plant is creating a massive amount of steam that they need to run their turbines and create electricity. But they're also basically pumping up to the surface gas, which is basically CO2. So unfortunately, they are producing CO2, however, not through the burning of fossil fuel. And so they need to do something about that CO2. And so they come with the idea is to take that actually and sort of combine it with groundwater. Iceland is really flush with groundwater, and inject it on the other side of the street from their geothermal power plant. So that's basically the plan. A cross section, again, that is your power plant. That's where the CO2 was supposed to come from. We laced it with a volatile tracer to see its movement later on in the underground, in the groundwater flow in the aquifer. We added our water to it. We carbonated it. You know now how it works. And we added to that water also some radioactive tracer to see what would happen actually to our carbon dioxide. Okay, and so we injected it here into the underground. And this slide is actually a really neat one to show that in order for this to take off, in order to show that a field study can actually really work, you need a playground. And for all that's tons of infrastructure. I'm not talking about the geothermal power plant. I'm talking about here a well, a deep well, injection well that was already drilled. And here we've got monitoring wells. They were already in place. So basically, because we did it in a geothermally active area, we were able to save, apart from of course harnessing a lot of the expertise, we were able to save tens of millions of dollars of infrastructure that would otherwise have been required to be drilled. Okay, good. So and then we injected roughly 500 meters depth, way shallower that you would need for supercritical CO2 injection, where you need to go at least 800 meters deep to keep the CO2 supercritical. Okay, good. So here it is. That's to PhD students involved in the project. So that's your water line, basically, and that is your gas line. Okay, and that where it comes together. Another slide showing that we had, of course, to take samples of the groundwater and see and measure, of course, bicarbonate, pH, and other geochemical parameters. And therefore, we had to do some, of course, testing how far actually that equipment that we developed specifically for this project would work. Okay, so here it is. That's your injection well. That was still before the injection, but to give you a more authentic view of Iceland and how it looks like, you know, even on a sunny day. Okay, and that's, you know, the Icelanders, they're really getting faced by snow blizzard, you know, they're really quite sanguine about it. Anyway, okay, so let's look at some results. And that's here the bicarbonate that I showed you, the dissolved inorganic carbon, but that's basically your bicarbonate, okay, over time. And you see after 400 days, basically, all the bicarbonate that we injected, boom, dropped. So that's what we injected, that's what we measured. And these are orders of magnitude. So based here on that difference, we came up with a conclusion that 98% of your bicarbonate had been precipitated, had basically disappeared from our groundwater. And with respect to C14, the tracer that we injected with it, again on a log basic, similar conclusion. After 400 days, a little bit over 1 year, 95% had gone. Okay, and so that was really great news, and we were able to sort of to sum it all up in a, like to call seminal paper. It's probably at a cusp of my career. It's not really getting better than that. Publishing in one of those high-cited journals. Good. Now, yeah, of course I could say that's it. It's great. Move on. That was it. However, and it's clearly for Iceland it worked, and they are still actually injecting happily ever after. They're still doing that. Okay. However, Iceland's just a small country, and they don't really produce that much CO2. And so, on a global scale, I'm afraid to tell you all, it won't make much of a dent. It's not going to cut it, basically. And the best proof is the slide. All right. So that is extracted from a report, the Global Carbon Capture and Storage Institute. That's an international think tank, and they're there really to promote all aspects of CCS. Okay, they have really vested interest in promoting, you know, that technology. Okay, and so basically you see here on the y-axis the storage, the annual capacity, right, over the last 10 years. Okay, so we have indeed operational units across all the world, including Iceland, and in total, if you go over there, they are able to sequester or store 40 megatons per year. That sounds a lot, okay? However, when you look at a report from the International Energy Agency 2015, data 2015, basically for CCS, here is, to make an impact, we need 80 gigatons of reduction through CCS. Okay, before the year 2050, that means in the next 3 decades, in a 2 degrees emission budget or scenario. What it means is to avoid an overall global warming of more than 2 degrees in the next 3 decades, okay, CCS needs to contribute, again, 80 gigatons storage of CO2. And I can't overemphasize the importance of this, because when you look at it here, actually when we go back and just pick the year 2013, from 2013 between in construction and operational, 40 megatons, up to now, last year, nothing has basically changed. And actually even in previous years, okay, 10 years ago, 11 years ago, they had even actually more projects in early and or advanced development respectively. So basically it hasn't really picked up. And when you look now at these are the annual capacity. So when you add them all up in the 10 years, basically, the world has stored a gigaton of carbon dioxide in the last decade. And so extrapolating that over the next 3 decades under the year 2050, that would make 4 gigatons. Look what we need. 4 gigatons, I know it sounds a lot. It's nothing, zilch. It's just not getting, we're not there, not remotely there. And this is why a lot of scientists like me, who have spent, as I said, over a decade in that field of carbon storage, we've come to the conclusion, okay, you know, perhaps we should actually really change tack and look for some alternative. Good news is, there's one. And that is actually replacing carbon dioxide with hydrogen. Now, you'd be excused if you can't really now follow that sort of, that leap of logic of replacing CO2, which is basically an exhaust gas, a sewage gas, with a very valuable hydrogen. Why would we actually inject hydrogen in there? And reason is that we are using renewable energies, not burning fossil fuel, but ideally using a lot of renewable energies down there, right? And we are using, that renewable energy to split water. That's an endothermic process with a lot of energy, and when we do that, we're ending up with oxygen, goes in the atmosphere, no one cares about it, and hydrogen. And so basically, if we create a lot of hydrogen, especially during peak time, a lot of wind storms and high solar irradiation during daytimes and summertimes, we have massive amount of hydrogen that we need to store somewhere. Okay, and that's where storage, hydrogen storage into underground reservoirs comes into play. Okay, so it's called underground hydrogen storage. Now, underground hydrogen storage, now the geochemistry is actually equally fascinating, but from a different point of view. Before, when we talked about carbon storage, you remember it was about creating a carbonic acid and dissociating it. So it was acid-base games. Now with hydrogen, it is about redox reactions, because hydrogen is an electron donor. It can be oxidized. And you see that over here, from this publication, if you're unlucky, okay, it can be oxidized by iron-reducing bacteria. It can be oxidized by sulfur-reducing bacteria. It can be oxidized by reducing carbon dioxide and creating methane in the presence of methanogens, that is microorganisms. It can also be actually consumed, oxidized, in the presence of acetogens into acetic acid, okay, or acetate, okay. So there are numerous ways to complicate hydrogen storage, or actually rather sort of thwarting our plans in storing hydrogen by, unfortunately, consuming it. I mean, there's really no reason in spending again millions of dollars injecting a valuable resource into the underground if it turns out that part of it may be consumed by microorganisms, because they just love to take that electron away from hydrogen. Okay, and so just to give you an idea about how recent actually all these events are, there is our first international webinar that was held in May this year, so 4 months ago, okay? And it was all about the microbial influence on hydrogen underground storage, because that will be key to understand all these, reactions and interactions, okay? Is it going to be rather reduced by these bacteria, those bacteria? What are the bacteria going to do with hydrogen? Now, the good news is, to finally finish that off, is that there are also recent publications that say, okay, wait a minute, I understand that you may actually reduce the methanation, okay, your hydrogen. However, in the presence of divalent of ferrous ion, however, actually, that oxidation, so basically your divalent ferrous ion, okay, which is oxidized, can help reduce water into hydrogen. Boom. So suddenly, we're not only having microbes who may unfortunately oxidize your hydrogen and create protons and or water, we may also have, at least in the presence of ferrous ion, okay, of a reduced form of ion, actually possibilities of creating additional hydrogen through the reduction of water. So you see, it's a very dynamic field, a lot of chemistry or geochemistry happening, okay, and we're just at the beginnings of it all, understanding, coming together. But clearly, takeaway message is carbon storage is not entirely dead, but it's just not getting us there where we want. However, harnessing renewable energies a lot, finally, and using it to good use in the sense of creating hydrogen that we could later then use is perhaps the way forward. Okay, good. Thanks a lot for your attention.